I attended university for 14 years. I have a bachelor's degree in mathematics, an associate degree in electronic technology, a certificate in electricity. I also have half of a master's degree in electrical engineering, 3/4 of a PhD in physics and instrumentation, 3/4 of a PhD in plant physiology, and a smattering of mining engineering and civil engineering and electrical engineering. But then after I graduated, I worked for the College of Mineral Sciences at the University of Utah for 3 years and helped develop the bioextraction program for Kennecott Copper. And that's where I started gathering the mining experience and expertise. After that, I've simply learned what was necessary to understand the geology up here and the mineralization and how it worked. And of course, the chemistry and the physics helped me design a system to extract the ore that is very, very efficient and much more effective than anybody else in the mining industry has ever developed previously. To help fund the mine, a guy called me up and we had an hour-long conversation about the mine, and at the end of the conversation he says, this sure sounds like the Drum Mine. And I said, yep, that's the one. He says, I've got some documentation on the Drum Mine that I've had in my files for years that you might be interested in. And so I gave him my email address, and half an hour later this document shows up that was an exploration survey by the U.S. Geological Survey. And what they had done is they had come up to this mine and the area around it, and they had collected over 1,000 samples of ore, and then they had analyzed them for 30 elements. That's the type of exploration survey that if a private party, contracted to have it done, would have cost $2 or $3 million. And so it was absolutely wonderful. And that was a professional job. They took the GPS reading and the full description of every sample they picked up, so you could go back and find the same material. But what that survey showed was that the gold was just literally the tip of the iceberg. That the other minerals, the copper, silver, 24 other metals, were worth 10 times as much as the gold was. And all of a sudden, everything changed, because now it was no longer a gold mine. Now there was tons of value. There was no overburden. The expense fell through the floor. And so, we started working on a process to recover all the metals out of the ore. We came up with an absolutely incredible process that cost 1/3 of what any other company, a mining company in the world, has to spend to process the ore. We've got the processing cost down to $8 a ton, at the same time that we recover all the oxidizable metals. We can recover over 60 metals, including all the platinum group and half the rare earths out of the ore. And so at the same time that our processing cost went down by 1/3, the return, the benefit that we got out of the processing went up by a factor of 10. And so the whole world changed from night to day. All these streaks of color, yellow, green, blue, purple, red, orange, and brown, are streaks of mineralization. Everywhere you see that color, that means there's high mineral content to the material. Okay, so what I'm going to explain is how the ore body formed. The ore body is called a jasperoid, and what happened is when the whole mountain range was tipped up to the northeast, it broke right in the middle of the mountain and formed a fault zone where there's 6 parallel faults that run all the way across the mountain chain. They're about 50, 60 miles long. There's 6 parallel faults in that zone. And when the mountain chain broke in the middle, it allowed the hot volcanic acid solution to come up through those faults. And one of the things they came into contact with as they came up through the faults is a bed of limestone. The acid causes limestone to dissolve, go into solution, so it disappears, and then the minerals and the quartzite precipitate out of solution to replace it. So it's called replacement altered rock. And what happens is that underneath the ground you'll have these pocket zones where there's nothing but water, and during an earthquake you have vibrations that come along, and so the cavity expands, for a fraction of a second. And and that forms a vacuum, and so the water in that pocket flash evaporates. And when it evaporates, then it can't hold the minerals. And so the gold, is left behind when it evaporates. Then the water condenses again, after the vibration is gone, but the gold is left behind. So you have these tiny, tiny grains of gold, and then they become the seed crystals around which the iron pyrite forms. The iron pyrite and the quartz forms. And so you have these micron-sized grains, that are the gold, that are left in the rock as it forms. Anyway, so what happens is that there's a hole in the ground, in the fault, where the water comes up through, and that's like the trunk of a tree. So the water comes up, dissolves the limestone, spreads out and forms the canopy of the tree, and then it will break through the bed of limestone in one spot, and a branch will extend up, and it'll dissolve more limestone and form another branch. And so each of these jasperoids that you're seeing are like the top of a tree that's buried in the ground. The bottom of the trees are 600 feet deep, because that's where the water came through the fault at. Okay, and so they're cone-shaped, so in open pit mining, that's ideal, because the farther down you go, the smaller the ore body is, but the higher the mineral content is too. So it's a wonderful mining situation. But as you look here, what happened was these are the tops of the jasperoid, and they were once all buried, but what happens is the precipitation, rain and snow, comes down onto the ground, and it seeps into the ground, and it reacts with carbon dioxide and forms carbolic acid that causes the limestone to dissolve. And so the land in between the jasperoids subsides, lets down, and that's why these individual outcroppings show just like the top of a forest, is because the ground around the jasperoid has been settling down as the limestone dissolves underneath the ground. And so as you look out there, that's exactly what you're seeing, is the top of a jasperoid forest. Anyway, that's one of the characteristics of the jasperoid, is it precipitated out a solution. So everything in that rock is a crystal of one type or another. Okay, and so the types of crystals that fracture on a plane will have a high reflectance in them, and so lava rock has no crystals in it, and you'll never see any particles of the lava rock reflecting light.